All right, well, good afternoon, everyone. So I'm going to be speaking about a fairly long-running program where we trigger target of opportunity observations to focus on potential impactors and very close Earth flybys. I'll talk about some of the motivation and the goals of this program, give an example of some of the things that we're finding in this population, and then talk about some of the sort of future directions, I think, for these types of studies. So project overview, as I said, we're conducting telescopic observations. These are characterization observations trying to understand physical properties of newly discovered objects. So we wait for objects to be discovered and then follow them up with a variety of assets. And we're focusing particularly on potential impactors and things that experience very close Earth flybys. And this program was really motivated about 10 years ago, started by Rick Binzel and Alan Tokunaga at the IRTF, motivated by the 2008 TC3 impact, realizing that there's a need for rapid response telescopic characterization for these highly interesting events. And typically for the targets that we're looking at, we have about 24 to 48 hours of advance notice from sort of initial discovery by the surveys to when we actually can the windows in which we actually can observe these things before they either become too faint or in some cases actually impact. So the goals of the program, number one is really to establish observational protocols. So we use very close encounters as test cases to be able to establish the techniques and methods that we want to employ to be able to observe these objects, which, as I'll talk about later, are actually quite challenging targets to point a telescope at and characterize. So we want to understand how the telescopes work and how these systems work to be able to effectively do these types of observations. We are also collecting physical properties on objects down to Chelyabinsk size. So we're able to build over time sort of population statistics of the physical properties in a size regime that is hard to probe. And then lastly, we are looking at non-impactors. Some of these objects are very close flyby objects. And in those cases, we're interested in what goes on in terms of physical properties during these encounters. There's a number of lines of evidence, both from models as well as observational data that suggest very close encounter NEOs can actually experience physical changes. And those changes in physical state, whether it's rotational or spectral, those can inform our understanding of the physical properties of these bodies, things like internal structure and surface properties. So the observations that we carry out are primarily photometric light curves and visible and near-infrared spectroscopy. These are the three main telescopic assets that we currently use for this program. On the left-hand side, we have Lowell Observatory's Discovery Channel telescope, or the DCT. In the middle, we have the SOAR telescope in Chile. And then, as I said, this program started at NASA's IRTF in Mauna Kea in Hawaii. So we have a geographically distributed sort of network, small network of telescopes here that are relatively large aperture facilities that allow us to do these types of characterization observations for targets that can be quite faint in some cases. So the large aperture definitely helps. And the geographic distribution of these assets is valuable as well to be able to protect against weather losses and things like that that might affect the ability to carry out these types of observations when you only have, say, 24 hours to do them. So data products, we collect visible wavelength photometry. This is an example of one of the light curves that we collected on one of our target of opportunity objects from last December. So we're using these data, the shape and amplitude of the light curve tells us something about the morphology and elongation of the body, sort of coarse information about shape. The variability tells us about the rotation period of these objects. We're also collecting spectra, and the spectra allow us to constrain composition. So here's an example of a composite visible and near-infrared spectrum from back in 2016 for one of these target of opportunity objects. We can use spectra like this to assign compositional analogs, for example, by comparing to laboratory spectra of meteorites. That allows us to constrain density of these objects, and ultimately that has sort of the pragmatic effect of in the case of an impactor, reducing uncertainty on what the impact energy would be. And that's effectively through spectral relationships with albedo. If we are not able to actually measure an albedo for the object, or we don't have, say, a neowise detection of the object, we can use these correlations between spectral types and albedos to constrain diameter. And through the compositional link and density inferences, we can get a mass. So these observations are challenging. And this sort of GIF is an example of why these objects are hard to point the telescope at, and in some cases even have the telescope keep up with the object. These things can have very high rates of motion on sky, and in some cases can actually exceed the accurate tracking rates of some telescopes. And finding those limits, what telescopes can actually track and keep up with these things, is an interesting operational experiment to undertake. Because these objects are so new, it is sometimes the case that they do have large ephemeris errors, and it is not always straightforward to point the telescope and find the object in your field of view. Hunting can sometimes be required. These objects can be quite faint. They're being discovered oftentimes at the limits of discovery surveys. So we're talking about 20th magnitude objects. There's only so much you can do when you have such faint objects in terms of characterization follow-up. And then sort of something that is both a positive and a challenge is that the number of targets that we have available has increased dramatically. When this program started 10 years ago, we knew of about 10 objects per year that were passing inside of half a lunar distance. And now, because of the efficiencies of the discovery surveys and how good they are getting at discovering objects, we're now looking at some 40 or so objects per year that are passing inside of half a lunar distance. And that's sort of what we use as a threshold for a close encounter. So, with 10 objects a year, that's a lot, but it's something a small group of people can reasonably deal with. As we're getting up to many tens of objects, this population of sort of interesting objects for study is getting out of control. And so there's a thought that needs to be put into how to deal with the growing catalog of objects and growing catalog of events that we might be interested in following up. So here's just an example of one of our flybys from summer of 2018. This was a noteworthy flyby because it was actually observable on both sides of the near-Earth encounter, which is not always the case. Many of these objects fly by and end up going by off in the direction of the sun, and so we can't actually see them pre and post flyby. But this one we actually were able to see both sides, and its rate of motion on sky was actually quite high, so it was sort of an interesting operational test. How effectively can we track and characterize an object like this? And we had a number of challenges associated with this observation that highlighted some vulnerabilities in the telescopic systems, but we did get useful data. We got spectral information that constrained the size, and the rotation rate of this object turned out to be remarkable in that it shows periodic variability of 10.8 seconds. So this is the fastest known rotating minor planet in the solar system, I think, still. So it's a very, very rapid rotator, but for an object of this small, it's not too extreme, but it is something that's interesting to find because it is pushing sort of the limits of what we can actually detect with these ground-based facilities. So looking ahead, there are limits to what we can point telescopes to for the reasons that I highlighted previously, and I think we really need to start giving serious thought to how to more effectively target and characterize objects very early after their discovery. So when they're still in the NEOCP stage, and/or they have sort of poor or high errors associated with their ephemerides. We need more facilities to be able to do this. This is just 3 telescopes that we've been employing for the past number of years to be able to do these observations. I think it would be valuable to expand the capabilities of this network. We need to deal with the situation of the number of known events increasing dramatically, and that's only going to become even more pronounced of a problem as next generation surveys come online. And then, for really short notice events, Davide talked about 2018 LA. We only had 8 hours, and there was really not an opportunity to get on sky to characterize that object in any way. And that would have been incredibly valuable if we could have gotten, say, spectral data before the object impacted, because meteorites were recovered in that particular event. So there's a need to figure out how to bridge that gap a little bit better. And then again, with future surveys, that's going to significantly influence the number of events available to follow up. So for the particular program that we're running, we do a few events per year, typically inside half a lunar distance. We also target low delta V objects. The data products allow us to constrain morphology, rotation period, and composition. I didn't really talk about this, but I think there's great value when these data products can be combined with others collected by others in the community. Things like albedos or radar data or even additional astrometry or polarimetry. For these sort of high priority targets, it's great to learn as much as we can in the short windows that are available. And then lastly, I just sort of finish on the note that, 10 years ago, we weren't really ready for 2008 TC3. No really large telescopes pointed at that object before its impact, and that was too bad. I think we're in a much better place than we were 10 years ago, but there's room for improvement. And essentially, we want to do this more, better, faster. We want more telescopes, the ability to target more objects. We want better quality data coming off of these telescopes, and we need to be able to respond faster. So with that, I'll take any questions. Thank you.
Thank you. Do we have any questions? No questions, huh? I would comment that TC3, we actually got about the best light curve data, but that was from the school observatory in Massachusetts that we just happened to get on to.
That's right. I mean, it was fortuitous that data were collected of TC3, and it was not large apertures, which was fine because the data turned out to be quite interesting. But I would say the professional community was maybe not as prepared as we should have been.
It was too bad that the whatever year it was, AA or something like that, happened on New Year's when everybody was out drinking or whatever they were doing. Gerbs.
Yeah, hi Nick. I'm just wondering, do you also check the PCCP? And do you do rapid follow-up for things that might look extended, even if they're...
So typically the follow-up that has been done for this program is all post-MPEC. We rarely do any NEOCP follow-up, and that is partly an operational decision. So for example, it is non-trivial to take the IRTF and point it at an NEOCP object. It can be done, but the overhead in doing so is extensive. And when we're interrupting a telescope schedule to take over time from some other observer, we want to be efficient and we want to do it quickly. And so oftentimes I don't think to date we've ever triggered an NEOCP object. So we typically wait for an MPEC to come along and then move forward. With that said, we can get the groundwork or lay things out so that if we think something on the NEOCP is going to be interesting, we'll inform people that something could be coming in the next 12 hours or something like that.
Thank you.
Okay.